Hi, everybody. I hope you had a great weekend. It's Friday, actually, here in Shanghai. It's a little dreary, but I figured I'd get the video done a little bit early. If you look on the schedule, we're wrapping up equilibrium and torques, and we've done a lot with rotational inertia. But I'm going to get a little bit ahead of the game and actually get into rotational kinetic energy. Rotational kinetic energy, just another type of energy, just like all the rest, just like uh, kinetic energy, gravitational potential energy, elastic potential energy. Um, this is a new type, though, stored in rotating objects. The equation for it is remarkably simple. If you take the original equation for kinetic energy, 1 half mv squared, and replace the v with omega r, it becomes this equation right here. Uh, but you probably very quickly realize, wait a second, m times r squared, that's just I, or the definition of rotational inertia for individual masses. And so this is just the total rotational inertia, I. So you can rewrite it this way, 1 half I omega squared. And so this is called rotational kinetic energy, RKE. You can also write it just as, where's my pencil? As just regular old K. So you can just say, all right, now we've got kinetic energy can either be this form of kinetic energy, which is the regular linear form that you're familiar with, or it can also take this case of a rotating object, also has kinetic energy of a different type. Spinning objects or a rolling object like this, if it's rolling around the floor, moving around like this, has both omega and it has a velocity, v. And so objects that are rolling on the floor, what kind of energy do they have? The answer is they have both linear kinetic energy and rotational kinetic energy, RKE. So what can we do in this, or what can we do with this? Sorry. It's actually quite useful. As we're trying to modernize the electric grid, the great difficulty with solar and wind is that it's rather unpredictable. For example, with wind, you can have solid hours of wind. That's wonderful. The steam generating plants shut themselves down or shut down a few boilers, but then just as quickly the wind can stop. And now the problem is, how long does it take to get a boiler back up at the power station? The answer is usually about an hour to get the water hot enough to boil. And so what do you do in that meantime? Just doesn't work very well. So what have power companies been doing? Even with solar and wind, they'll keep the generator and the boilers operating full time, even with a minimal load. A few years ago, it's now almost 10 years ago, some companies realized, wait a second, we could actually store the energy in the form of rotational kinetic energy. And what they've done here is taken huge flywheels, that is, rings basically with all their mass at the outside edge, and they're made out of carbon graphite. And they put them vertically in these cylinders that are at a vacuum, and then have a motor that can spin them up to high speed when there's excess electrical power. And then when the grid needs power, like for example, a cloud goes over your solar panel, the wind stops blowing, you can use the stored rotational kinetic energy in these disks to actually keep the power going. So I've got a quick question for you. Actually, I've got a video here. If you have this downloaded, you can actually click on it. All right, I'll show it to you. If you don't want to watch it, you can skip the video at this point. Oh, maybe I can't play it. Sorry. So here's the question. According to the specs, each flywheel rotates at 1600 RPMs and stores 90 megajoules of energy. My question is what's the rotational inertia of one of these rings, of these cylinders that are sitting inside of here? How do we solve it? Well, first of all, we've got to convert this 1600 or 16,000 revolutions per minute into something nice, radians per second. So just doing a little bit of factor label or unit conversions, getting rid of the revolutions first of all. Each revolution is equal to 2 pi radians. And then I need to get rid of minutes, and we know each 1 minute is equal to 60 seconds. If you divide that through, you'll end up with roughly 533 pi radians per second. What's the formula for rotational kinetic energy? It's just 1/2 I omega squared. So plugging in our numbers, we know the energy stored is 90 million joules, megajoules, equals 1/2 I omega squared. And if you solve this real quick, you'll discover the rotational inertia is about 64.1 kilogram meters squared. If we knew the exact shape of this, we could even calculate its mass. We'd need to know the radius as well. So another quick example, working backwards. In this case, I want to ask you, what's the rotational kinetic energy of the Earth? Sort of the maximum energy storage on the planet. Just think about the rotation of the Earth itself on its axis. Well, first of all, you have to remember that we've got to do a little bit of conversion. The omega for the Earth goes through 2 pi radians every 1 day, 1 rotation each day. Doing some factor label conversions, getting rid of days. 1 day is 86,400 seconds. And if you work that out, you'll get roughly this many radians per second. I didn't leave it in terms of pi this time. How do we solve this one? Next piece, we need the rotational inertia. Well, the rotational inertia of a solid sphere is 2/5 mr squared. Where's that from? From that table in your chapter. Plugging in the numbers, you get the rotational inertia of the Earth, which is incredibly large. Last step, just a plug and chug, 1/2 I omega squared. And if you plug that in, you get a ridiculous amount of energy stored in the rotation of our planet, 10 to the 29th joules of rotational kinetic energy. I know it's an approximation. The Earth is not uniform in density. So this equation is not perfect, but this gives us a relatively close answer. That video clip you just saw was the first jet being launched off the new U.S. Navy's aircraft carrier called the Gerald Ford. Why were they so excited? Instead of using a steam catapult like all carriers used up to this point, that was its first test of its electromagnetic catapult. If you've been at some amusement parks, you've felt these before. These are the ones that sort of launch you horizontally without a hill. It uses electricity. The problem is it uses a lot of electricity to launch a jet like that. How do they do it? Well, it turns out even the nuclear power plants and the generators on the ship can't generate enough electrical power for this quick takeoff. And so what they do is they do the same trick we saw 2 slides ago. They store it in large rotating cylinders under the deck. According to the specs, they're initially spinning at this speed, and then they slow down to this speed after the launch, and they release 121 megajoules of energy. So the question is what's the rotational inertia of the cylinders? So our first step is we're going to have to convert both of these into radians per second, our sort of standard unit. So our initial omega, just working it out, revolutions per minute, doing the conversions, converting revolutions to radians, and then minutes to seconds, you end up with roughly that many radians per second. Doing the same thing with the final angular velocity, you end up with roughly that. So we know that in this case, the energy released was due to the change in the rotational kinetic energy. In this case, actually the loss in rotational kinetic energy. So normally when we try to find the change in something, we always take the final minus initial. But because in this case we're looking for the loss in the rotational kinetic energy, I'm going to reverse this, take the negative of delta RKE, and take initial minus final. Now it's just a matter of plugging in some numbers. So our change in energy, the amount of energy released is that much. 1/2 I omega initial squared, we got that from up here. And minus 1/2 I omega final squared, which we got from right here. Solving it, you'll discover the rotational inertia from the published data is 1,590 kilograms meters squared. Why am I suspect on this one? Remember the commercial model used to store energy from the grid? That was about 60. This thing is over 20, oh my goodness, more than 20 times larger. which seems suspect. My guess is either these two numbers are not correct in the documentation, or they're using multiple ones to generate this amount of energy. This number does seem amazing to me. All right. The more likely problems you're going to run into are these. So in this case, we've got a disk that's a cylinder sitting at the top of a 3-meter tall hill, and it's going to roll down and then roll across this horizontal piece down here. The question is, when it gets down here, what kind of energy will it have? And you're like, oh, duh, kinetic energy. Yeah, but it's also going to be rotating. So it's also going to have rotational kinetic energy. And you might say, wait, Mr. Clymer, didn't we do some problems like this where we did, and in the energy chapter, where we did GPE equals KE? Yeah. I tried to make sure in those problems that I made the objects relatively small, so the rotational inertias were a small fraction. But yeah, you're right. Technically, we didn't account for the RKE in that chapter because we didn't know about rotational inertias yet at that chapter. And so all of the answers in that chapter were just a little bit off. I promise no other hidden types of energy in this book. But now we can actually do this properly. So when I ask you what's the velocity at the disk velocity at the bottom of the ramp, how do we solve this one? Well, we know that the energy initial plus work equals energy final. Remember the energy conservation one. In this case, the initial energy is just GPE, and the final energy is going to be the KE plus the RKE. Plugging in the equations, we know that mgh equals 1/2 mv squared plus 1/2 I omega squared. And the question is, what's I for a disk? Well, if you remember, a solid cylinder is a disk, and you look it up in your table, you'll discover that that equation is 1/2 mr squared. In this case, we know the mass of this thing is 2, the radius is 0.05, and so I becomes this. So we're expanding this out. mgh equals 1/2 mv squared, v we don't know, plus 1/2 I omega squared. And you're like, oh great, we can solve. Well, we got one issue here. We've got v and we've got omega. We've got two unknowns. You're like, no, this is horrible. But again, just like we did when we were solving some of the earlier problems, you might remember there's a direct relationship between omega and v. From your Rosetta Stone, you've got this equation. Rearranging it, omega is equal to v over r. What can I now do over here? I can replace the omega with v over r. And now this actually works out pretty nicely. Solving that equation, you'll discover everything over here cancels for the most part. And I end up with 1/2 times 2 is 1. That squared over that squared, yeah, just gives me 1/2 v squared. Gives me this, or if you solve that, you'll discover the velocity of the disk at the bottom is 6.26 meters per second. And that is completely correct with no approximations. All right. This time we've got a solid sphere rolling down a hill of height 40 meters. And the question is, what's the velocity of this solid ball when it reaches the bottom? If you include its RKE. And you're like, wait a second, you didn't give us the radius or the mass. Could you please pause the video? And I do mean it. Normally I have you work in class with a buddy. Could you try finding the velocity? Set up the equation. I'll give you the equation first of all. Plug in what you know and see if you can solve this. Please pause the video now. I'm going to count down from 3 and then I'll talk through the rest. But I do want you to try it first on your own. 3, 2, 1. So plugging in our equations, of course, looks like that. And doing our substitutions, the rotational inertia of a solid sphere is 2/5 mr squared. Doing the replacement for omega, I'm going to replace it with v over r. And if you do that, you end up with just, whoops, I think I had this one in the wrong order, sorry. Oh, wow. You end up with just, the m's cancel. in each of the terms. So you'll end up with just 293 equals, and this should be 1/2 v squared plus 1/5 v squared. So you get 7/10 v squared, and you end up with a velocity of 23.7 meters per second. I've got a feeling this next part of the equation is going to pop up afterwards. Yeah, there it was. The piece we were missing. It's just in the wrong order in the animations. I'll fix that later. It also works in reverse. If you've got a ring, in this case it's a hollow ring, rolling at 5 meters per second, what height will that ring reach before it stops briefly, before rolling back down on the top of this loop? So here's our ring briefly stopping before it rolls back down again. How do you solve it? Again, with just the energy equation. In this case, it starts out with KE and RKE, and it all ends up as GPE. Plugging in our equations, we end up with that. The rotational inertia for a ring is just mr squared. And plugging in V over R for omega, just so we can solve this a little bit easier, we get that. Oh, I went backwards again. And you end up with the height. After you quick solve this one, you can cancel out the m's in all three terms. 1/2 plus 1/2 just gives you v squared equals that, and your height it's going to roll up to before stopping 2.55 meters. Oh, there's another piece missing. Oh, it's definitely out of order. Oh, a brain break. It's about time. All right, each answer in the grid below is a word or name that contains the consecutive letters tick, tack, or toe. Each is used exactly 3 times. Every line contains tick, tack, and toe except for one. All right, so let me get you started on this one. To kill a bill, that one's easy. That one's a veto. Wait a second. It doesn't actually have toe in it. I thought it had toe because I had these. I may be wrong on that one. Let's see. Oh, okay, let me do this one then. Boston basketball team is definitely the Celtics. Does that work? Oh, yeah, tick. So that's got tick in it. And I'll do one more. Tex-Mex shell is a taco. That's the tack part of the tic-tac-toe. Tic-tac-toe. Maybe it's vetoed. Ah, that would work. Now I've got toad, and I got tick, tack, and toe all in one line. Could you please try the other ones if you would like? I'm going to do a quick countdown of 5. If you want to work on this for a second, just take a break away from the physics. Pause the video. Otherwise, 5, 4, 3, 2, 1, go. It was vetoed. Celtics taco. Crustacean tiptoe. Tiptoe got me. Antarctica, mortician. That's an old word. Antacid, and of course photoelectric, which is easy if you've done engineering, but all right, moving on. Angular momentum is our other topic I want to get into. Angular momentum is one of the big conserved quantities in all of physics. Remember our conserved quantities? Conservation of momentum, conservation of energy, and our final one is conservation of angular momentum. Ironically, we spend an entire chapter on momentum, an entire chapter on energy, and we're only going to spend a small section on angular momentum. I feel kind of bad. Angular momentum is profound. It's probably even more significant than most other things, and it probably deserves its own chapter, but we're just going to spend a little time with it. A quick note, Elmer Sperry. The problem with plane flights. So you might say, what does this have to do with plane flights and angular momentum? Let me quick explain. As most of you know, if you want to fly to China anywhere from the U.S., what's the shortest route? Well, it's the part of the Great Circle. It's a circumpolar route that takes you up near or pretty close to the North Pole, depending on where you're flying, and then back down again if you're heading here to China. But these flights were never taken that direction until about the 1940s. Why? The device that Elmer Sperry invented. Most people have played with a little gyroscope toy before. You get this spinning really fast, and it will balance on a stand if you put it here without tipping over. Why? It has angular momentum, which has to be conserved both in terms of magnitude and direction. Elmer Sperry realized, wait a second, we could use that same device to create what we call nowadays a gyroscope. He put a motorized gyroscope, or one of these little tiny gyros, inside here in something that was free to rotate on multiple axes. So even if you rotated this case, this would always spin in the same direction. And it would always want to spin the same direction because once it had angular momentum, it didn't want to change direction. Why was this profound? Well, let me go back to the airplanes. It turns out, even back before the gyroscope was invented, you could easily fly north. You just follow your compass. The problem is, once you're up here, every direction is south. And so you could fly north, but once you got close to North Pole, everywhere was south. And so you could end up going up this way and saying, oh, yeah, I'm good. I'm heading south to China and end up in Europe or Russia or, heaven forbid, the middle of the Pacific. Once you had the gyroscope, what you could do is before your plane took off, you could point the axis of the gyroscope north, get it spinning, and now as long as the gyroscope spun, it would always point in the same direction, and you could actually plot your course. Sperry became a millionaire, one of the first millionaires, just based on his very simple invention. And ironically, and I've got this little video clip here to show you, he actually hated plane flight. He always took trains or cars, but he used his ideas in the gyroscope for a really fun sort of practical joke. He had a special suitcase built which had a set of batteries in it, a high-speed gyroscope, and a motor that would get it spinning. And he had a small switch hidden in the handle. He would actually put it down, and I got to kind of draw this. The train would be like this. This is back in the good old days. He would set his suitcase down here on the ground, throw the little switch, and then would go over to stand over here at the door of the train while he would watch the porters try to move it into the train itself. Now, I got to quick explain. Gyroscopes, once they're spinning, don't want to change direction. In this case, the gyroscope was spinning, so the angular momentum vector was pointing that way. What did it mean? It meant that you could easily move the suitcase this way without a problem, or even this way, or lift it up or put it down without a problem. But the moment you tried to twist it, either one way or the other, that would change the direction of this angular momentum vector, and the suitcase would perform very strangely. In fact, it would sort of tilt up in midair like this. And you're like, wait, what in the world's going on? Sperry would watch the porters play with this, trying to figure out why in the world it was difficult to turn, and when you did turn it, it actually lifted itself up in the air. And then eventually he would go, excuse me, is there a problem? And the porters would say, yes, there's something really wrong with this suitcase. It's possessed. At which point he would reach down and throw another little hidden switch in the handle, which hit the brake on the gyroscope, at which point he could very easily turn it and move it into the train. He was a bit of a practical joker. All right. The equation for angular momentum looks like this. Just a quick reminder, regular momentum is a vector. It's equal to the mass times the velocity vector. And so the momentum points in the direction of velocity. If you simply translate this into its rotational equivalent, the rotational equivalent of velocity is angular velocity, which does have a direction, times rotational inertia, which is the equivalent of mass. And the letter we use for angular momentum, my apologies in advance, is capital L. So that is our angular momentum. And this is the general equation for it. It turns out you can also write another equation for it. Remember that omega, I should probably solve it real quick for you, just to prove the other one for you. If you just have a point particle, that is just an object. Here's the center of curvature. It's moving around with some radius r, and it has a mass m moving with some velocity v. Please realize you could rewrite or find its angular momentum this way. We know it's I times omega. But for a point mass, remember from the definition of rotational inertia, rotational inertia is just mr squared. And remember, we could write omega as v over r. And I don't know if you can see this real quick, but 1r cancels out, and we just end up with mvr. But the r here is very important. It's got to be perpendicular to the velocity. If it's not, you'll have to find the component of it that is. Otherwise, these two pieces don't work right. And so for a point particle, you can use just this equation right here. Or if it's not exactly perpendicular, you can take r sine theta. Sort of like what we did for torque. You can also write this as m omega squared r, or sorry, m omega r squared. Although we typically don't use that one nearly as often as simply this one right here. The analogies, angular momentum, linear momentum, torque is equal to the change in angular momentum over time. Force is equal to the change in momentum over time. It's conserved if there's no external torques. This one's conserved if there's no external forces. You've seen this in action before. I don't know if I can get the ice skater playing or not here, but if you've seen an ice skater pull in her arms, what's happening? You'll see that her omega gets much, much larger. Here she starts out with a small omega, but she has a large I. Why? Because the mass of her arms here is very far away from her rotational axis, r. This increases her I. When she pulls her arms in, now the mass is much, much closer than it was before. What does that do? It makes the I smaller. But because the angular momentum has to be conserved, her omega becomes much, much larger. She spins faster. Angular momentum I times omega. Initially, I's big, omega small. Afterwards, I gets small, omega gets big. The total angular momentum has to be conserved. Just like before, when we did regular momentum, you've got a before and after picture. The angular momentum beforehand, big I, small omega, has to equal the angular momentum afterwards, small I, big omega. All right. Let's try an actual problem on it. Sorry, this one's a little bit messy. It's hard to see. Let's say in this case, the person's torso by itself has a rotational inertia of 7 kilogram meters squared, and this person's initially spinning at 3 radians per second. They also have 2 5 kilogram masses that are 1 meter away from their axis of rotation initially. Afterwards, he pulls it in so it's only 0.1 meter, or these masses are only 0.1 meter away from that. We're going to ignore the mass of his arms and just pretend that his rotational inertia stays at 7, but it's going to change because we move these masses in. So how do we solve this one? Well, we know the angular momentum, this is before and afterwards, has to be the same. So angular momentum beforehand has to equal angular momentum afterwards, which we know is equal to, angular momentum is equal to I times omega. So I initial times omega initial equals I final times omega final. And now plugging in our numbers. The total rotational inertia beforehand is the person plus the masses times initial omega equals the rotational inertia of the person plus the masses afterwards times the final omega. Plugging in our numbers, the rotational inertia of the person is 7. And each mass here is just mr squared. So 5 kilograms times 1 times 2, because there's 2 of them, times the initial omega, which is 3, that was given, equals the final. The rotational inertia of the person still stays at 7. But now our 2 masses, our 2 5 kilogram masses, are only this far away from the center, and there's 2 of them, equals omega final, or times omega final. Solving it, omega final should be about 7.18 radians per second squared. Or sorry, radians per second, not squared. You can tell I'm getting tired. Let's do another quick problem. If you've got a point particle of radius r moving, or mass moving at velocity v, you can, of course, just write it as mvr. I already proved it to you. Normally, I would prove it right here. How'd you calculate omega? Well, omega is going to be equal to, if you remember, V over R. And what's the rotational inertia? Oh, sorry. I'm so sorry. This is going to be mr squared. This is rotational inertia I, not L. I'm solving L down here. L is equal to I times omega, or you can very quickly see it right here. If I again plugged in mr squared, the I, times V over R for omega, you end up with just mvr. All right. Wanted to show you this real quick.
The right, of course, is a magnet, and the one on the left is just a pencil, and we had no idea they were going to decide to mate.
We're still waiting the results, man.
Just to show you that, yes, even objects that aren't spinning initially do have angular momentum. You could see that after the two objects met, they were both traveling at regular linear velocity. When they met each other, they began spinning. They did have angular momentum. So MVR can actually have angular momentum. So a couple quick sample problems. You've got a baseball and it's about to hit this bat. The bat is 1 meter long. This is the pivot point down here where you're holding it. Imagine the person's hand holding it right there. The question is, what's the angular momentum of the ball relative to this pivot point? So how do you solve that? I'm going to use just the specialized point mass equation. And if you plug it in, just m, the mass of the baseball, 150 grams becomes this, times its velocity, is here, I actually reversed it, times the radius 1, gives us 4.5. And the units here, I forgot to mention what the units for angular momentum are. If you work it out real quick, I has units of kilogram over meter squared, or sorry, kilograms times meter squared. And omega has units of radians per second. What happens when you multiply these two times each other? You'll end up with kilogram meters squared over seconds. And you might say, whoa, wait a second, what happened to the radians? Remember, again, radians is a unitless thing. It's remember, arc length over radius. And so this should have units of that. What's the angular momentum of the ball relative to the point where it hits the bat? It, of course, is 0 because the R in this case is 0. And again, the units are that. All right, this one's a little bit more exciting. What's the angular momentum of the student relative to the center of the merry-go-round before he runs on? So what we've got here is a student who's running along here, and hops on a stationary merry-go-round. I don't know if you ever played with one of these. They're actually one of my favorite playground toys, but there are so many injuries, they've removed them from most playgrounds. How do we figure out the angular momentum of the student? She looks like she was running perpendicular to this thing, so how are we going to solve it? We're just going to use MVR. In this case, her mass, 65, times her velocity times the radius of this thing, gives us her angular momentum, which again is kilogram meter squared over seconds. Treating the merry-go-round as a uniform cylinder, find the resultant angular velocity. Assume the student lands on the merry-go-round while moving tangentially to it. So assume she's standing right here on the edge. So how do we solve this? Well, angular momentum has to be conserved. In other words, what was the initial angular momentum? It was just the angular momentum of the student. What's the final angular momentum? It's the entire merry-go-round and the student rotating around. Solving this one gets a little bit exciting. So we know the total initial angular momentum is 832, equals the rotational inertia of the ride plus the student times the final omega. Plugging in our numbers, this we're going to assume is a disk. Remember the formula for a disk, 1/2 mr squared. And the student is going to be like a point mass, just that mass times how far she's standing away from the center, 1.6 meters squared, times the final omega. Solving this one, you should end up with a final omega of about 2.71 radians per second. Two ice skaters. This one's a little bit hard to visualize. So initially you've got two ice skaters and they're each holding on to the end of a 10-meter long rope. One ice skater spinning this way, the other ice skater spinning this way. And then what they're going to do is, and they're spinning around this point right here. And a moment later, what they're going to do is pull in on the rope so that now suddenly they're much closer. As you can quite imagine, their eye is going to be smaller, which means their angular velocities are going to have to get much, much larger. But the question is, what's the period of this new motion? All right, so solving this one. This one's like one of your textbook problems. Solving it, we know the angular momentum has to be conserved. In other words, I initial times I initial times omega initial has to equal I final times omega final. And now here's the tricky part. We're going to go back to some of the definitions. Remember that omega can be written as 2 pi over the period, where the period's how long it takes to go around once. It'll go through 2 pi radians in that amount of time. If we use that equation, sorry I drew over the top of it, we can write this equation. The rotational inertia is going to be the mass of each of the two skaters times how far they're away from the center. In this case, they're each 5 meters away from the center before they get started, or before they pull on the rope. There's two of them, so 2 times mr squared, times the omega, which in this case is 2 pi over the period 5 seconds. Where is that 5 seconds? Oh, I forgot. Oh, every 5 seconds, there it is. Equals the final I, which is going to be 2 times m times 1 squared. If they're 2 meters apart, it means that the r's here are only going to be 1 meter now, over t, which is what I'm trying to solve. And if you solve this one, you'll discover the period is 0.2 seconds. In other words, 1/5 of a second. If this was around, they'd be spinning around 5 times per second, a crazy, ridiculously fast speed. And now, if each skater had a mass of 75 kilograms, what's the work done by the skaters in pulling closer? How do we solve this one? This one's a good old work energy one. The initial energy was their initial rotational kinetic energy. Their final energy is their final kinetic energy. Just plugging in the numbers, 1/2, and this whole part right here is the I, initial, times, remember, omega squared. So again, remember the difference. In this equation, it's just I times omega. For rotational kinetic energy, it's 1/2 I omega squared. Two different things. This is RKE. I times omega is angular momentum L. 1/2 I omega squared plus the work done equals the final 1/2 I omega squared. And if you solve this one, you'll discover a crazy amount of work, over 71,000 joules of work to pull them in that close. All right. Angular momentum, just a little bit more on that one, does have a direction. There's a right-hand rule here. If you remember omega, if this is omega, and if you remember, if you could curve, and I'm going to try to hand draw this, if you take your right hand and point your fingers upward, oh, this is going to be bad, sorry. And that is a horrible hand. If you've got your right hand and curl your fingers in the direction of omega, your thumb points in the direction of omegas, the vector, the direction of omega itself. So in this case, if this wheel is rotating this way, omega is pointing in this direction right here. And since angular momentum is equal to I times omega, whatever direction omega, the vector points, is the direction that the angular momentum vector is going to point. What does that mean? Well, if you look at the girl standing over here, let's assume that this thing is spinning this way initially, and its angular is spinning, I guess I should draw it along here, is spinning this way. And so its omega is pointing upward and its angular momentum vector is pointing upward. She's standing on a turntable down here. If she suddenly flips this over, she'll start spinning. What's going on here? I've got the person sitting this time. The total angular momentum beforehand has to equal the total angular momentum afterwards. The problem is now after you tip the wheel over, its angular momentum is pointing downward. Now, how can that ever possibly be equal to what it was originally, both in terms of magnitude and direction? Well, the answer is the person themselves then are going to have to start spinning this way. Why? Because that way it gives, this is the person's angular momentum vector. This is the wheel's angular momentum because we tipped it upside down. It has the same magnitude as it had before we started, but now it's going in the opposite direction, so its L is pointing downward. And now what happens is this. The sum of these two angular momentum vectors, remember how you add vectors? Person plus head to tail, new wheel one, gives us the resultant, and this resultant here is equal to the initial here. So the total angular momentum is conserved. So you can actually begin rotating yourself just by turning the wheel upside down. We'll do this demo when you get back. Remind me if we haven't done it already. It also explains Kepler's second law about planets sweeping out equal areas in equal times. Why? Angular momentum has to be conserved. The mass of the planet stays constant, but what happens here? When you're at a large r away from the sun, your velocity, if this is big, v has to be small. When you come close to the sun, r gets smaller. I could draw a tiny r. And so your velocity has to get bigger. Since this has to be conserved, as one changes, the other one increases. And because it's exactly relational, if you make r twice as big, velocity becomes half as big. It'll sweep out equal areas in equal times. And at this point, I'm going to stop for the night or day, depending where you're at. And we're actually ahead in the chapter, which is a great thing. I'm going to send the links out here. I'm also going to let you know I'm going to set up office hours from 10 to 11 a.m. Shanghai time on Wednesdays and Fridays Shanghai time. For those of you in Korea, that should be about 11 till noon on Wednesdays and Fridays. For those of you in the U.S., it'll actually be Tuesday and Thursday nights on the East Coast from 9 till 10 p.m. And it gets a little bit earlier on Tuesday and Thursday nights if you're further west in the U.S. I'll send out that link along with this video. Have a great time. Keep sending me questions as you run into them, either by email or WeChat. And again, remember to submit your textbook problems in the drop boxes. Talk to you soon. Bye.